Alright, welcome to lesson 2-4b. This is the chain rule part 2. So now that you're a little bit more familiar with the chain rule and you've seen how we can use the chain rule to find the derivative of a composite function, now we're going to take that just a little bit further. So while sometimes the chain rule is all you'll need, oftentimes you'll encounter a function that's even more complex, that it's not just a composite function. It might be a product of two functions where one of the functions is a composite function, or it might be a quotient, or it might be some other variation where you've got more than just the chain rule happening. So that's the purpose for today's lesson. So we're just going to look at some examples where the chain rule isn't the only rule that's going to have to come into play. All right, so taking a look at our first example. So here we have y equals x squared times the square root of 1 minus x. So very first thing I'm going to do, and this is pretty much a general rule, as soon as you see that you're dealing with a function that involves a radical and you're trying to find the derivative, the very first thing you should be doing at this point is rewriting the radical as an exponent. So the very first thing we're going to do is rewrite this function as y equals x squared times 1 minus x to the 1/2 power. Okay, so like I was saying in the intro, today we're looking at examples where the chain rule is going to be part of the process, but not the only rule involved. And so I've read this function aloud a couple of times, and both times when I said it, hopefully you notice that I said it's y equals x squared times 1 minus x to the 1/2. So what we should recognize then is, first and foremost, this function is a product. It's the product of x squared times 1 minus x to the 1/2. And because its overall form is of a product, then that means to find the derivative, we should be using the product rule. So that means we're going to do y prime equals, so again, the product rule, as you know, it's going to be the first times the derivative of the second plus the second times the derivative of the first. And so up to this point, when you've seen me do this step a lot where I'm just showing that we're going to take the derivative, some of you have asked, do we need to show that step moving forward? And the answer is no, you don't have to. But today is one of the reasons why I encouraged you to get used to doing that. Because now that we can see where we're intending to find the derivative within this product rule, hopefully now you notice that to use the product rule, when I'm finding the derivative of 1 minus x to the 1/2 power, that right there is a composite function. And therefore, this derivative right here will involve the chain rule. So now we're going to find y prime equals, so again, it's going to be the first times. Now, to find the derivative here, using the chain rule that we've been discussing, so that means my u, my inner function, is 1 minus x, and it means that my y is going to be u to the 1/2. So that means the derivative here is going to be 1/2 u to the negative 1/2 times the derivative of 1 minus x. Plus, and then we've got that 1 minus x to the 1/2 still. And then we have this nice easy derivative of x squared, which is just 2x. Let me change that color there. So let's go ahead and finish off this chain rule that we were doing here in the beginning. So I've got y prime equals x squared times, and again, that's going to be 1/2 times, now I'm going to go ahead and replace that u with the 1 minus x to the negative 1/2 power times the derivative of 1 minus x, which is going to be 0 minus 1, or just negative 1. And then again, we've got plus. I'm going to go ahead and move this 2x in front, since that's a more conventional way for us to write that expression. And then in that first term, I'm just going to go ahead and combine some stuff here. I can multiply the 1/2 and the negative 1, and then I'm going to move that negative 1/2 in front of the x squared because it's a coefficient. So finally, I'm going to write this answer as negative 1/2 x squared times 1 minus x to the negative 1/2 plus 2x to the 1 minus x, sorry, 2x times 1 minus x to the 1/2. Now this is technically our answer. That is the derivative using the product rule with the chain rule inside of it. Now, however, further down the line, and I don't mean way down the line, just a little time from now, we are going to need to work with this expression a little bit more. So again, for now, for our purposes of making sure we can find the derivative successfully, this answer right here is fine for now. But I do want to show you where you are going to have to be able to take this shortly. So right now, there are a couple of different ways we can do this. I'm going to do this through factoring. Now remember, we technically have two terms here. We have negative 1/2 x squared times 1 minus x to the negative 1/2, and then we have a 2x times a 1 minus x to the 1/2. And when we factor, so first of all, I've got a fraction. I'm going to factor out that fraction. So a negative 1/2 gets factored out. Here I have an x squared, and in the second term I have an x, so I can factor out an x. Here I have a 1 minus x to the negative 1/2, and here I have a 1 minus x to the positive 1/2. And you may recall that when you factor out a common factor with exponents, it's the lowest exponent that gets factored. So all of that was my my greatest common factor. Now, what does that leave us with? Remember, when you're factoring out a GCF, you're dividing the original expression by that. So if I took out the negative 1/2, that's gone. I took out a single x from an x squared, so that is going to leave me with just an x. And I took out a 1 minus x to the negative 1/2, so that's completely gone as well. So that entire first term, all I'm left with is an x. Now be very careful here. I factored out a negative, which means this plus now becomes a minus. Again, if I were to distribute it back, it would have to give me a plus. So since I factored out a negative, that now has to also turn to a minus in between the two terms. Now here's a slightly trickier thing. That 2, remember, if I factored out a 1/2, I'm technically dividing by 1/2. So 2 divided by a half is the same as 2 times the reciprocal, so 2 times 2 over 1. So this now bumps up to a 4. And again, if you just check that real quick, if you distributed it back, negative 1/2 times negative 4 would give you a positive 2. All right, we had an x. I factored out an x, so that's gone. I had a 1 minus x to the 1/2, and I factored out a 1 minus x to the negative 1/2. And if you recall, when you factor out powers, you end up subtracting the power that you took out from the original power. So this is now going to be 1 minus x to the original power, 1/2, minus the power we took out, which is a negative 1/2. But if I do 1/2 minus a negative 1/2, that's actually 1/2 plus 1/2. So that now becomes the following: x minus 4 times 1 minus x to the first. I should be using brackets there. Okay, so this is now technically to the first. And because it's to the first power, I don't need the exponent anymore. And because this is just to the first power, I can now distribute that 4, which I wouldn't have been able to do if this was any power other than just a 1. So continuing to simplify here, I now get negative 1/2 x times 1 minus x to the negative 1/2 times x minus 4 plus 4x. Now we've got negative 1/2 x times 1 minus x to the negative 1/2. And then in here I have x plus a 4x. That's going to give me a 5x minus 4. Now this is much closer to what we want. Again, this would be a much better answer than the original one that I had, but we can do one more thing, and again, there will be a very good reason for us to do this later on, is that negative power, and I've got a denominator, we're going to rewrite this entire expression as a fraction. So in the numerator, I'm still going to have that negative, I'm still going to have that x, and I'm still going to have that 5x minus 4. So in my numerator, I've got negative x times 5x minus 4. And in my denominator, I'm going to have that 2. And then remember, if I move this 1 minus x to the negative 1/2 to the denominator, it makes my exponent positive. And this is the form of the answer that we would want. And you would be welcome, of course, to change this back into a radical, but there's not really a need to. So this is what your goal should be. And what I would encourage you to do is, in WebAssign, feel free to type this as your answer. But on your work, on your paper, attempt to get to here. All right? So that way, right now, you can still get your full credit by correctly finding the derivative, but you'll also be practicing in preparation for when we actually have to get to an answer more like this final one that I have here. All right, so let's look at another example here. So this time we have y equals x over the quantity x squared plus 4 to the third power. So again, when we read this function to ourselves, hopefully you're recognizing that this is a quotient. So we're going to have to use the quotient rule. Now, quick comment before I continue. Could you rewrite this as x times x squared plus 4 to the negative third power? Could you do that? Of course you can. And if that's the case, now this is a product rule instead. And so now this would resemble what we just did in example A. But because you've already seen me do this whole kind of a process using the product rule, I'm going to go ahead and skip this approach just so you can see what this would look like using the quotient rule. Now, why would we choose to do the quotient rule when it's so much more work? Well, sometimes it might actually make it a little bit easier to get to that final form that you saw me show in example A. So that would be maybe the benefit to doing that. All right, so let's go ahead and do the quotient rule. So y prime equals, so again, it's going to be low, so x squared plus 4 to the third power, d high, so the derivative of x, minus the high, so x, times d low, so the derivative of x squared plus 4 to the third power, all over low, so all over x squared plus 4 to the third power squared. So there's our quotient rule. So now let's go ahead and start whittling away at this. So within the quotient rule, I've got x squared plus 4 to the third power, oops, that got a little bit messy, times the derivative of x, which is just 1, minus, we have an x, times, now right here, the derivative of x squared plus 4 to the third power. We should be recognizing that that is going to require the chain rule. My u is x squared plus 4, and my y is u to the third. So the derivative then of x squared plus 4 to the third power is going to be 3u to the second times the derivative of x squared plus 4. And again, this is all over the denominator, which I'm going to write as x squared plus 4 to the sixth. Remember, to the third, to the second, multiply those powers. Let's finish off that chain rule then. So we're going to get y prime equals, now right here, times 1, so I'm going to get rid of that times 1. So I've got x squared plus 4 to the third power, minus, now here I have that x times, so now let's go ahead and clean this up a little bit. We've got a 3 times our u squared. I'm going to go ahead and replace the u back with x squared plus 4. Again, squared. And then times the derivative of x squared plus 4, which is 2x. And this is all over that denominator, x squared plus 4 to the sixth. All right, this is starting to clean up pretty nicely. So I've got a 2x times a 3 times an x. So let's see, x times 3 is 3x. 3x times the 2x gives me a 6x squared. So now I have y prime equals x squared plus 4 to the third minus 6x squared times x squared plus 4 to the second, all divided by x squared plus 4 to the sixth. Okay, now continuing on. In the numerator, notice that in the numerator I now have two terms. That x squared plus 4 to the third is my first term, and 6x squared times x squared plus 4 to the second is my second term. And in those two terms, hopefully you recognize we do have a common factor of x squared plus 4. The lowest power of those is 2. So we can factor out an x squared plus 4 to the second power. And that's now going to leave me with, now in the first term, remember we had x squared plus 4 to the third power. I factored out to the second power, so that's going to leave me with one of those x squared plus 4s. Minus, now in the second term, I factored out all two of the x squared plus 4s, so all I have left is the 6x squared. And then this is all over that denominator. And so now, if you notice, in my numerator, I've got x squared plus 4 to the second, and I have an x squared plus 4 to the sixth in the denominator. And these are factors, so I can cancel out those two factors of x squared plus 4 with two of these factors, which would drop this down to a fourth power. And then in the brackets, we can simplify there. I have an x squared minus a 6x squared. So that's now going to become a negative 5x squared plus 4 all over x squared plus 4 to the fourth power. All right, last example. So here we have y equals the quantity 2x plus 5 over x minus 1 all to the third power. Now this is slightly different from the previous example. In the previous example, we overall had a quotient, and then within the quotient, we needed to use the chain rule. This time is a little bit different. What I'm hoping you recognize is that this function here is actually first and foremost a composite function. This is really y equals u to the third, where u is 2x plus 5 over x minus 1. And what that means then is, first and foremost, we're using the chain rule, but then within the chain rule, when we find the derivative of u, we'll have a quotient. So this is a little bit of a reverse of what you saw in part B. So I'm hoping that at this point you can recognize that whether you use the chain rule first or the product or the quotient rule first, there is no one rule for which one you're going to do first. It completely depends on the way that the function is written. So for this particular example, the outermost form of this function is a chain rule. So that means we're going to use the chain rule first. So y prime equals, so it's the derivative of u, so that's going to be 3u squared, times the derivative of u. So the derivative of 2x plus 5 over x minus 1. All right, so that means, so y prime equals, so 3u squared, but my u is 2x plus 5 over x minus 1, so I'm going to go ahead and substitute that back in. So I've got 3 times my u, so 2x plus 5 over x minus 1 to the second power, and then times, now to do the derivative of u, again that's going to be the quotient rule. So I have low times the derivative of high minus the high times the derivative of low all over our low. All right, continuing on, so I've got 3 times 2x plus 5, over x minus 1, quantity squared, times, now over here let's go ahead and find these derivatives. So I've got an x minus 1 times the derivative of 2x plus 5, which is just a 2, minus, and then I've got 2x plus 5 times the derivative of x minus 1, which is just 1, and that's going to all be over x minus 1 squared. All right, moving on. And also, I'm going to go ahead and do this step now. You might not quite know why I'm going to do it. I'm going to go ahead and rewrite this. Remember, if I have a fraction to a power, this is the same as the numerator to that power over the denominator to the same power. So I'm going to go ahead and do that now. You might see why I'm going to do that, but if you don't, you'll see in just a moment. Now, in the numerator, let's go ahead and simplify. So I can distribute that 2, and if I do, that's going to give me a 2x minus 2 minus, now remember, I'm subtracting the quantity, so minus a 2x, and then minus a 5, all over x minus 1 squared. Now, hopefully you notice the 2x's are actually going to cancel out. And then I've got a negative 2 minus 5, which will be a negative 7. Let's move this up here. So I've got y prime equals, so I have 3 times a 2x plus 5 squared times a negative 7. This is over an x minus 1 squared, and this is also over an x minus 1 squared. And so finally, when I put this all together, I get y prime equals negative 21, 3 times negative 7, times 2x plus 5, quantity squared, all over, well, I had 2 x minus 1's here, I had 2 more x minus 1's here, so that's over x minus 1 to the 4th. And that is our simplified answer. Okay, so once again, the chain rule will oftentimes show up, but sometimes it won't be the only rule to use. Sometimes the chain rule gets used in conjunction with other rules, such as the product rule or the quotient rule. So these were just a few examples showing you what that looks like, but also this gave you some examples where you could see some of the algebraic work that we have to go through to get our answer into a form that looks something like this. Because oftentimes we are going to need our derivative to be written as a single fraction or as a single expression, not a sum of expressions, but as a single term. All right, good luck.